Well, all right, everybody. Part 4. So let's do a data analysis, right? So let's look at what happened here. Here's what I did. I'm going to do all the work for you. Just stick with me. I did 15 shakes of the dice through the dice tower for each of these, and I did it 1, 2, 3, 4, 5, 6, 7 times. Okay. This then turned that into averages. Now these might look funny if you're really like uptight about integers, I guess, right? Because the idea of 18.7 of these little cubes is kind of silly, right? What's a seventh of a piece of dice, right? But it's going to let us get a little more accurate, so I kind of like it. It's on average after 7 goes with this on the first trial, 18.7 of the 100 dice disintegrated, right? So what are we going to do with all this? Then I come over here and I stuck it into this, what we've used in the past. So it says number of students, but I guess this year we don't have students, we just had dice. Because we all couldn't be together. Time. What I'm saying is that this takes me about a minute. It took me about a minute to dump the dice, sort out the ones, put those in a jar, and take all the others and scoop them into a regular bin. And then another minute, then put them all in. It would take me a minute again to do that. So I'm saying each trial is about a minute of time. All right. This total number decayed. So then what I did was I chucked the numbers in from this spreadsheet. That's how many decayed each round. This column we don't really need, honestly. It just made the math over here a little easier. That's just cumulatively how many of them had decayed. Yeah, and then over here, this is really the number we need is percentage wise. When did we, how much did we lose? So I should probably make this bigger, but I don't know how to do that. What if I just make the font bigger? Is that going to screw us all up? No, it's doable. All right. Cool. So what do we want to look for? Let's go over to the lab. So if the data was perfect, clearly if you do this with math, you start with 100%, you divide it in half, you got 50, then you divide it in half again, you got 25, and so on, right? With this data, how long did it take to do each of these? And this is where we find out if these numbers like kind of worked or kind of didn't. So 100%, well, there was 100% at the beginning. There was all 100 dice. So making my font a little smaller. That's going to be after 0 minutes. That's right away. Now, let's keep in mind we're talking about radioactive decay here in real life, right? So if you want to do carbon dating on a tree, this would be like when the tree grew. It's 0 years old. And then if it gets buried in the right conditions where it can still be tested years later to see how old it is on the scale of thousands of years, that will be what we're like looking down for how many of these isotopes have gone away through time. So after 0 minutes, our beginning is 100%. Then let's look and see when did we get to 50%. So let's go back to Excel. When approximately did we get to 50%? So right about in here somewhere, like between 3 and 4 minutes. So maybe we'll estimate that that's about 3.5 minutes. What do you think? Now, if things working, that should really repeat itself over and over and over again. It took 3.5 minutes to get rid of half of the dice. It should take another 3.5 minutes to get rid of half again to get down to 25%. Let's see how we did. 25% is right about there. That's 7 minutes. It worked, lo and behold, which is great. All right, so in 7 minutes, we lost half. Now, again, let's try to predict. That would mean that this is at about what, 10.5 minutes or so when we got to 12.5%. Let's see. So that'd be somewhere in there. And look at that. It worked again. Wonderful. And if it worked again, if I want that low, did I go to 6.25? I did. What would that be? That's 16. Let's see. Sorry. I should do these at the beginning of the day, not at the end of the day. So at 6.25, where are we? We're somewhere in here at about 13 and a half. So does that work? I feel like I'm doing something wrong. Okay. Sorry. I wrote 12.5 here when it was 12.5%. That wasn't after 12.5 minutes. At 12.5%, we were at about 10 and a half. I think I just typed it wrong. Amy makes mistakes nice and easy, which again, that works. That makes sense. That's another 3.5 minutes in between those. So now when do we hit 6.25? It'd be right about in there at about 13.5. All right, so maybe a little bit tighter. But again, I think if I did more trials in future years, I'm going to have all the students do this. So we'll end up with however many students I have, maybe like 80 trials, which will be a lot better than 7. So 3.5 minutes passed in there. And another 3.5 passed there. In other words, every 3.5 minutes, we would expect to lose half of the remaining dice. Now that one came down to 3 minutes. Again, little bits of inaccuracies I think we can live with. What if we average those up to get what the real half-life is? 3.5. Coffee. 3.5 over 4 is 3.375, 3.4. So maybe every 3.4 minutes, if I start with any number of dice, I would expect to, of 6-sided dice, I would expect to, if I'm rolling them every minute, lose half of them in 3.4 minutes. All right. So what the heck am I talking about here? How does this relate back? I hope this doesn't get too far outside of like what we're really trying to do. So if we go and we find a tree from the Ice Age that managed to get buried in sediment and preserved to some degree, we can go into that. We can see how much carbon-14 is left relative to its decay product from the reference tables, which is right up here, relative to its decay product of nitrogen-14. And if we know that every 5,700 years we lose about half of it, it becomes really quite simple math to say, okay, there's this much left, therefore this tree must be about this old. These numbers are very verifiable and repeatable. This is like constantly studied. It's been studied by many people, and it continually works. These like atomic, I don't want to say atomic clock, that's the wrong way to say it, but these like radioactive decay rates are very stable and preservable. Here's some questions you might see, and here's some things to keep in mind. It doesn't change for any reason whatsoever. If you heat it up, if you cool it down, it doesn't change. If it's at high elevation, at low elevation, doesn't matter, doesn't change. These rates are very stable. They're just a matter of basic chemistry. It's